We have another example problem here. The charge in the bottom right corner of the figure, this capital Q down here, is negative 10 nanocoulombs. What are the magnitude and direction of the force on Q? So Q is being affected by both this 15 nanocoulomb charge and this negative 5 nanocoulomb charge. I'm going to label them as 1 and 2 simply so we can use an F1 and an F2. I'm erasing that so we can draw the vectors in without a problem. So again, since these are point charges, we're going to use Coulomb's law, which allows us to find this force, the electric force specifically, on a point charge due to another point charge. All right, so F1, let's see if I can draw a fairly straight line here. Charge 1, my 15 nanocoulomb charge up in the top left corner, that one's positive while this Q is negative. So these charges are going to attract. I'm only going to draw the force that Q is experiencing though, because that is the charge we want to find the overall force on. This force, I'm going to call it F1, points directly towards that 15 nanocoulomb charge. So it has a negative X component and a positive Y component, which we could draw over here in our little triangle. So the magnitude of F1, we use the K, the two charges involved, which I do need to put these in coulombs, so I have to put the 10 to the negative 9 in for nano. I am only going to put in the magnitude of this charge Q, because I'm finding the magnitude of the force. Magnitudes are always absolute values, so I'm not going to put the negative sign on. Okay, we need to know how far away those two charges are. We need to know this distance R, which we can get from, Let's see if I can get that kind of lined up again. R we can get from knowing the dimensions of this rectangle. We know this side is 3 centimeters. This side is 1 centimeter. They meet at a right angle. So using Pythagorean theorem, we find this is the square root of 10, but I do want to write this in decimal form because I'm going to have to convert it to meters. So it is 3.16, not 3, 23 centimeters. And again, I use a few decimal places since I'm not at a final answer. That is the distance that's going to come over into our equation up here. Let me give myself a little more room. So R squared in the denominator. Let me plug all these numbers in. I'm finding this force is 1.3485 times 10 to the negative 3 newtons. So this magnitude represents how long this force vector is. We will need to write this vector in terms of its x and y components in order to add it to the force vector that is created, the force created by charge 2. So let's go ahead and write this in terms of its x and y components. This x component is to the left. It is adjacent to this angle right here. So that angle, we have two ways to go about this. We know since this side is adjacent, the magnitude of this side will be f1 cosine theta. So we can go ahead and find out what theta is, and we need to do that using the dimensions of the triangle again. So theta, I know the sides, so I could say the tangent of theta was 1 over 3. So 1 centimeter over 3 centimeters. Inverse tangent of 1/3 gives me an angle of 18.43 degrees. And so I can totally take our magnitude f1 and multiply it by the cosine of theta. But I do need to put in negative because I know it points to the left. So the magnitude times the cosine of this angle minus I hat is that direction to the left. The y component, this side is opposite, so Fy is F sine theta. So we take the magnitude F and we multiply by the sine of this angle we calculated, and that is the y component. So F1 would be, just plugging these numbers in, negative 1.279 times 10 to the negative 3 in the x direction, plus 4.264 in the y direction. Oh, sorry, my power's wrong. Times 10 to the negative 4. So this is all in newtons. Now, a quick side note for those, some of you have learned in statics, we could totally look at the dimensions of the triangle. Instead of taking cosine of this actual angle, which is totally valid, that's what we just did, we could look at the dimensions of this triangle and see that cosine is the adjacent side over the hypotenuse. And put this in for the cosine of the angle, because that's what the cosine of the angle represents, or is in terms of the dimensions of the triangle. When we take the magnitude of the force times that ratio, we get this 1.279. Similarly, the sine of this angle would be the opposite side over the hypotenuse. So the R. And we could take this ratio and put it in for sine, and we would come up with this 4.264 times 10 to the negative 4. I just wanted to mention both ways because one way might be easier for you than the other. But either way, we have to write this force in terms of its x and y components, which we now have. So this is specifically the force that the 15 nanocoulomb charge is exerting on Q. We know the negative 5 nanocoulomb charge is also exerting a force. I'm going to call that force F2. Well, because both of these are negative, that means they are going to repel. That means Q is going to be pushed away from the negative 5 nanocoulomb charge. This direction's easy. It's just all in the negative y direction. So plugging the numbers, I'm using Coulomb's law again. Plugging these numbers in, I know K, the two charges involved are the 5 nanocoulombs and the Q, which is 10 nanocoulombs. I'm only putting in the magnitudes because I'm going to account for the direction in the r hat. So the distance between them is 1 centimeter, which I need to put in meters. And then r hat, I know the direction is completely in the negative y direction. So I'm going to just put that in. I'm getting, the negative sign comes from the direction, 4.495 times 10 to the negative 3 newtons. Excuse me, the negative j hat is the direction. Now, by the way, you might notice if we had put a negative sign on both of the charges, because they were both negative, we would still need to put that negative sign in for the direction. Make sure your answer and the direction it is written in, it totally makes sense in terms of the problem. If we had put the negative signs in and then did not put the negative sign on the direction, we would get a positive answer, and the positive answer would mean that force was upwards, which changes the whole problem. So we just want to be careful in terms of the directions. Plus and minus is always directly related to the direction of the vector. So we now have these two forces, F1 and F2. Q, overall, the force it is experiencing is the summation or addition of these forces. So the total force on Q is these two vectors added together. Well, remember, we can only add x components of vectors to x components of vectors, and then y components can be added together. In this particular problem, only F1 has an x component. Y components, when we add these together, so I'm adding this one and this one together, we're going to get a negative answer because F2 is bigger. So I'm just plugging in negative 4.069 times 10 to the negative 3. And again, negative j hat means the negative y direction, so downwards. Now we're not done. This is the total force on Q in terms of its components. That's not magnitude and direction like we've been asked for in the problem. Magnitude and direction means overall how long is the vector and what direction, what angle would represent the direction it points in. So if I draw this x component, This is our x component. It points to the left by 1.279. I'm going to just say millinewtons, since that's 10 to the negative 3. The y component points down by 4.069 millinewtons. So our overall force vector starts where I drew that x component and ends where I ended the y component. So magnitude means the length of this vector, force of Q, on Q, and an angle. So magnitude, we can use Pythagorean theorem. The 1.279 squared plus the 4.069 squared. Those are in millinewtons. So when I plug that through, our answer will be in millinewtons. So 4.3 millinewtons is the magnitude. The direction is the angle. So in my picture, I can say that my tangent of that angle is that opposite side over the adjacent side. So if I take the inverse tangent of that ratio, I'm getting 73 degrees. Now I can't say my direction is 73 degrees because this angle is always related to our polar coordinate system, which the polar coordinate system measures angles counterclockwise from the positive x-axis. So we could say 73 degrees below the negative x-axis. That would describe specifically where that angle was. Or we can add 180 degrees, which is 253. So approximately 250 degrees, that would be an appropriate way of describing the direction. For those that have taken statics, where you draw the axis and then the little arrow relative to the axis that the angle points at, that's also fine. But be careful in drawing this. You need to represent which axis and then an arrow tip on the line that represents the specific direction relative to that axis. So here is our answer. Magnitude and direction. And either any of these would work on a test. If you're doing the homework, it's going to tell you specifically where to measure that angle from. So just pay attention to that as you're doing the homework.